Cool. All right. It's 6 o'clock. Let's rock and roll. Got 87 of our best friends here. And so, yeah. Hey, everyone. Good to see everyone again. It's Wednesday, March 3rd that we're recording this. So I'm going to first talk about assignment 3. So hopefully you all have forgiven each other from maybe past transgressions. Maybe potential scam. Some enterprising student tried to message me on Discord and try to get me to sign their key. It did not work because I did not have a key for them to sign. So I thought that was pretty funny. It was a good try. So yeah, we'll be grading assignment 3 probably in the next week or so. We need to wait for every one of the keys to get in. But yeah, hopefully you got a little bit of if you developed a little bit of paranoia about who people are and thought about ways to scam people and to prevent yourselves from getting scammed. I think a really interesting thing, and usually what we do is we'll talk about, I'll try to ask some of the people that have that did really well on the assignment to try to get them to tell us their techniques, because it's probably things that you hadn't even thought of. I had a couple semesters ago, the students created their own certificate authority. So they had 2 of them that controlled the Google Doc that had real names of people that they verified, and they each would check their IDs. But one person, super enterprising person, hacked their way onto the list. I think just like social engineered them basically and pretended to be their adversarial key. And they got 20 or 30 adversarial keys, signatures from everyone that was on that list. So usually, and I don't know it for this class yet, but usually there's a long, a long tail power distribution of scamming where there's a few really good scammers and the rest of them are really tapers off. So, and it's usually not that one person gets scams a lot either. Usually the scams are pretty even, but we'll see that. So yeah, anyways, okay. So that's assignment 3. That'll be done. I hope that was a little fun change of pace. Now, of course, the second topic that you are concerned about is the midterm, right? So the practice CTF site is down right now because we're setting everything up for the midterm. So you will not be seeing, the practice site is going away. We'll be releasing the midterm CTF site sometime between the end of the class and midnight tonight. Who knows, it could take longer. If you've ever dealt with computer stuff, you know that sometimes it can take longer depending on weird problems that show up. So we'll do our best to get that to you. I'm not going to tell you any information about it because you'll know soon enough. Like if I tell you anything about it, of how many challenges, whatever, that's not going to change in the next 3 or 4 hours until it's released or whatever. So yeah, I'll announce on Piazza. So just be on the lookout for Piazza. I'll also have a write-up there. The important thing that I'll put in that write-up that I'll also mention here is kind of the fun part about having this CTF style midterm is that you can kind of see everybody's progress and as they're breaking levels and challenges. And one of the really cool things is then you can target yourself to try to solve the easier challenges because you can see what challenges have been solved by the most people. So that's pretty cool. And so that helps you target. The flip side is, of course, we have a scoreboard with how everyone's doing. And since this is it'll be a 1-to-1 correlation between your grade and what you're seeing on the CTF. If you don't want people to know that it's you and you want to hide your grade, choose a random user ID. All your user IDs went away. So those are all gone. You'll create new ones. So then when you create your hacker alias, if you don't want to be associated with you, just do something random. If you do, whatever, do that, but it's up to you. So I'll make that clear on the post, but I think that's all we're going to say about this now. Cool. All right. And yeah, so we're going to get started and start on network security. So we got a lot to cover here. We're going to, and the goal here, so you've gone over a lot of different topics, and that's kind of the goal of this class of 365 is that we're trying to expose you to many different areas of security. You went through crypto and authentication and authorization and access control and all kinds of cool stuff. So now we're going to turn to network security. So we are going to go into the details of how networking works. We're not going to go into every detail. So we're not going so deep that like you would do in a networking course, because obviously we don't have a whole course to cover this, but you will understand how packets are moving throughout the network from, let's say, me to you to other levels. So this will build a good base for you for that. And it really comes down to, and this is the, yeah, what's up? Is that a question? Okay, cool. So the kind of, and the really interesting thing is, so what I love about networking is we basically have like, so we have this problem where, and I'll use Zoom since we have this, right? So there's me, there's Zoom, right? I'm on Zoom. And how are the sorry, I don't think you guys have actually suffered through my handwriting yet, so I apologize right off the bat. But somehow, and we can see this is happening, right? Somehow data is coming from me, from my machine here, is going out on the internet from here to Zoom, and then going to all of your homes. So that's, it's something that's kind of crazy to think about. So we're going to study how this actually happens. And by the end of this, you will understand how data moves on that route. So, and we're going to look at all the things. And the really cool thing, and what I like about networking, is there's nothing magical here. There's, we should dispel you of the notion that there's any kind of magic in computing. It's all, everything is all knowable. And so, so in networking, requests for comments, or RFCs, are where you can find all the information and details about these networking components and how they work. So you can literally just read that to see how things work. So we're going to start with, and what we're going to be looking at is basically when we think of the internet. So what is the internet? What does an internet mean? Yeah, somebody want to put in the chat? Yeah, so actually internet stands for, that's great, an interconnected network, right? So an intranet is like your local, so think about your local area network in your house. If you have a Wi-Fi router that you're connected to, that's your local area network. And you're connected to an ISP. So actually we can start filling out this diagram, even with things that we know currently. So we have my machine here. I have I'm going to draw it like this. This is my Wi-Fi router. So I'm connected to my Wi-Fi router. There's other stuff here like my phone, I don't know, other devices. And all of this is under my ISP, right? So your internet service provider, you're providing some service. And then, so what are they doing? So they, if it was just, think about, so I have, right now I have Cox. So if the internet was just everyone who had Cox, which was kind of how actually early days of AOL had, where you could access and talk to other users of AOL, but accessing the internet was actually really difficult. So the internet comes in where all of the ISPs are connected to each other. So I'm going to draw them kind of as nebulous clouds here. So somehow my data is going from my machine to my router, out on my modem to Cox, which then sends it somewhere else. And then there'll be some other thing that goes in there, goes somewhere else, bang, bang, to somewhere else. And then finally over to Zoom, and then maybe back to you. So this is the reality of networking. And so how this all works is the Internet Protocol Suite. And if you think about it, this is a crazy difficult problem, because how many different operating systems and machines does everyone have, let's say, talking to the internet right now in your home? Like I have a Mac, I have my iPhone, I have my iPad right now. Somebody has a Windows machine, I hope. I have a Linux box somewhere in there that I use. I have my watch, my Apple Watch. What else does anybody? Yeah, I'm thinking of different types of operating systems, and all of those machines have to be able to talk to each other and exchange data over, yeah, good consoles, Xbox, a Switch, a PS4. Some people have refrigerators, a Chromecast, and Alexa. All these things are devices that need to be able to talk to each other. And so you have to have, this is one of the really interesting things, you have to have well-defined protocols of how data actually gets sent. Otherwise, you can't have any communication. You would only be able to imagine how horrible it would be if only Apple devices could talk to Apple devices, or only Linux devices could talk to Linux devices. That would cause massive problems. And so the suite of protocols are all kind of known as the TCP/IP protocol suite, and we'll talk about this in a bit. And the really nice thing here, and one of the things I want you to be thinking about as we study the design here, is thinking about these levels of abstraction and encapsulation. So these the IP stack is kind of built on these levels of different levels of abstraction, and each level and protocol handles a different thing. But again, everything is knowable. So there's protocols that handle at the link layer. So specifically, like actually my machine I'm using now is a wired connection. So it's a wired connection to my router. So how does the data that I'm sending go on the wire from my machine to the router? And then you have the question of how do we then cross packets? So that's how it goes, maybe one hop. How does it go multiple hops out of there? How does data get transported? And finally, we have applications at the top. So all this is kind of the classic model when thinking about the TCP/IP stacks. So at the bottom, we have the physical layer. On the top of that, we have the link layer. Above that, we have essentially the internet, or the internet protocol, like the IP layer. Above that, we have the transport layer. And then finally, we have applications on top of this. So this is kind of a crazy thing to think about, is to even get data from one machine to the other, you need to implement and handle all of these different cases. And then only when you do that can you do things like HTTP and DNS and NFS and SMTP. And one of the important things that this diagram should hammer home, one of my massive pet peeves and something you can do to make it very clear that you don't know what you're talking about, is to call the web the internet, or the internet the web. So the web is basically HTTP and hyperlinks, and that's just one application that runs on the internet. So, and just like, so SMTP, does anybody know what SMTP is for? Yeah, mail. So that's great. So it's a simple mail transport protocol. So emails emails actually predate the web. The web didn't come into existence until the early 90s, I think like 92, basically. Whereas we had SMTP before that. People were sending emails before they could ever visit a website, which is super cool. Now, there's actually a lot of complexity in here of how all of these things work. So going back to this diagram, we basically have kind of at the link layer trying to understand how data gets from your machine to anything else on the local network. The IP, as we'll see, is about how to get data from one machine to the other. And finally, TCP and UDP are different ways that we can transfer data, and we'll talk about that in a second. Yeah, so people are talking about blockchain. I think the pitch is that, let's say, or the goal, what people want is for blockchain to be another layer on top of here, especially if you think about Ethereum and smart contracts and those kinds of things, would be another layer that people build things on top of. I believe, I mean, it's got to be using TCP basically to do everything that it needs to do, especially Bitcoin. So Bitcoin has got to be at the application layer under TCP. Cool. All right. So, okay. Sorry, I'm skipping ahead. You all already know this stuff, right? Okay, cool. All right, that makes sense. I'm just teasing. Yeah, I was wondering about the order of this, but now it makes sense. Okay, cool. So the very first thing we need, so let's think about this, like this diagram. So I'll simplify it by getting rid of all that crap that I just added to it. But you have me, right? You have me, my machine here, and we have Zoom all the way on this other side. So you're designing some system for machines to talk to each other. What do you need to know first? Yeah, you need some notion of where do I send this data, right? How do I get, so when I say Zoom, right, I just said me and I said Zoom, but how do I actually get that data from me to Zoom? And actually a really good analogy that helps with this is think about, has any of you ever sent a letter in your life? Like mailed it with stamp and everything? Okay, thank gosh. I was a little bit worried. Yeah, so envelope, right? So you have the envelope, and on the front, so what are the things that you put on an envelope? So this will be the front. Yeah, so you need a stamp, you need to pay for it somehow. What else? The address you're trying to send it to and the name of the person. Since we're computer people, we'll send this to foobar, blah, 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 blah. How specific do you have to be on your address? Has any of you ever tested this? Yeah, so you need to specify the house or the location, right? So in the cities, the state, actually there's a fun fact. It used to be when towns were really small, and this probably still exists in a small town, you could, because the postmaster would know everyone's house. So you could say, oh, I'm sending this to Foobar, who's at the big red house past the cornfields. And they would, the local postmaster would probably be able to figure it out or ask around about who knows how to get to that letter. So anyways, it's kind of an interesting thing that we lost a little bit along the way. But so we can add this information, right? We can put a stamp, we can put the name, we can put the address, and here the address would have to have things like in kind of a large hierarchy, right? What state, what city, what zip code, and what street number on that street, and what maybe what apartment number even, so going more granular. Now this person, so Foobar got our letter, they want to send us something back. How do they know where to send that response to? Yeah, we're missing a return address, right? So I'll put myself here and I'll put squiggles for my address. And I've now put my return address. And so this actually has two features, right? So it's so that the person we send the letter to knows how to send it back to us. What's the second feature? Yeah, so who sent it is the first. What's another feature? Yeah, wrong address, right? So that the mail system can actually give it back to you. So that's actually the second thing. If the letter, let's say Foobar doesn't exist or that place doesn't exist, that letter can come back to you and they know where to send it because it has your address on it. Okay, awesome. We have exactly the same problem here in these computer systems. We have two computers. We want to send data from one to the other. And we can even think of data in this case as an envelope that we want to send. We want to send data from one machine to the other. What do we need? So do we need a stamp? Yeah, not really. There have been some proposals for doing like microtransactions on data that you send or whatever, but we need, so we don't have to necessarily pay for it, right? But what do we need? Yeah, so we do pay for it when we use the internet, exactly. And actually, if you want to think of how expensive the internet was, I was just doing some research. This is why I'm full of AOL details, but in like 95, an hour of internet from AOL at insanely slow pace that would make you gouge your eyes out, like 56K modem was $3.50 an hour, which I believe now is like slightly higher than, it's like 6.5 an hour for internet, for slow internet. It's crazy. So think about that, now when you're complaining about your ISP, and I definitely do as well. So, okay, so we have our, let's say, and let's, I like this little envelope thing. So we have our envelope here. What do we need to do to send this to Zoom? Yeah, I need to some address, right? I need to say, hey, I want to, and I'm gonna do it like this. So I need some way to say, hey, I want to send this data to Zoom, and here's how to get to Zoom. And I also probably want a return address as well, right? I want to say, hey, here's how to get to M and this. And we'll actually see that this is super cool. And all of the pieces that we've kind of been studying will click into place to allow this to happen. So this gets us back to the address. So we need to have, and we call it an IP address, right? This is what people talk about when they say an IP address. This is exactly what they're talking about. So each host, to be accessible, each host needs one or more IP addresses on each of its network interfaces. So here when we say network interface, a network interface could be an Ethernet port that you plug in Ethernet, or it could be your Wi-Fi adapter. It could be any number of things. And you've probably seen IPv4 addresses. This is what we're going to focus on. We won't touch IPv6, but IPv4 addresses are composed of 32 bits. What does that mean, and how many number of IP addresses are there possible? Yeah, 2 to the 32, right? Perfect. Awesome. Yeah, this is kind of classic CS math, right? So we have 32 bits of information. We can store up to from all zeros to all ones. So 2 to the 32 is the number of different IP addresses. Actually, in practice, it turns out to be less than that for several different reasons, which we'll briefly touch on. And it's typically these 32 bits. So this is actually, if we go back here, what we're doing if we were to, zoom in on this letter, right? So here I have my letter. I'm sending this letter to Zoom. I'm not actually putting Zoom, right? I'm putting some IP address, right? So 10011001001001001. It'd be really cool if I just wrote down 32 bits there. But anyways, so 32 bits here is actually what I'm sending. And that's super cool. So this is kind of crazy. So you can think about, to talk to any machine on the internet, all you need to know is a 32-bit integer. But how does that actually look in practice? Would it be super fun to write out the bits? 101101100001001. Is this super fun? Is everyone happy to write out binary? Yeah, no, we don't want to do that. So actually, it's like a weird happenstance. The 32 bits is separated into 8-bit octets. And then we represent in decimal notation each of the different octets. So the first 8 bits get represented at the start and turned into decimal. So this is the 149.169.175.207. So this is if you've actually, has anyone, hopefully you've seen an IP address before, maybe? I mean, people are putting them in chat. So I guess if you're completely ignoring chat, you haven't seen it. Yeah, so here's a crazy thing. So that IP address doesn't actually mean anything to the computer, right? The computer has to translate it into an integer. And it does that just by translating it like you do. A very fun fact. So people were talking about, there's some special addresses like, no, wait, no, that's not the one I wanted. Right. So this is actually the entire, and we'll talk about this in a second, but I think it's a /8. Anyways, anything that starts with 127 is your local machine. So this means this current machine that I'm on. So this is why if somebody's tricking you and saying like, oh yeah, hack into me, this is my IP address, they're actually hacking into themselves. Now, the super funny thing is many web services will block and say, if I see an address that's 127.0.0.1, I'm going to block it. Unfortunately, there's actually a lot of different ways to represent IP addresses. I don't know it offhand, but if you convert this into a decimal number, right? So 127 is a certain number of bits, 1, 2, 3, 4, 5, 6, 7, 8. That's definitely not right, but whatever. 16 zeros and then 5 zeros and then a 1. Whatever that number actually represents. What is it going to be? It's going to be something big. 2, 3, 7, 2, 6, 5, 0, 0, 1, 0, whatever. Whatever that, so translating it between there into an integer will actually, in a lot of software, will get you to local hosts. So you can bypass filters that are looking for blacklisting 127.0.0.1, which is pretty cool. All right. Cool. So this is the base of all addresses. So, and part of the problem is organizations need a range of IP addresses to use. So we're going to kind of skip over some of this, but anyways. All right. So I'm going to go with an example for this. Okay. Another 192.1. This is, I know, a /24, I think. No, I think it's 16. Anyways, okay. So, trying to see if I want to do this here or do this later. Okay. Yeah, we'll do this at right now. So, okay. What we want to do, so we're an organization. We want all of our IP addresses to be in a similar range, and we want to be able to tell what IP addresses are ours and what IP addresses are other people's. So that's like when I said here that 127.0.0.1. So let's say if I had a network where everything with the exact same first 8 bits are all inside my organization and controlled by my organization, I would call that a /8. So I'd say the first 8 bits of the IP address are the network ID. So it means my network ID, and the rest of them identifies the hosts inside my network. So if the first 8 bits are fixed, how many hosts can I have in my network? Yeah, so somebody said, a couple of people said 2 to the 24. Why would it be 2 to the 24? Somebody want to justify it? Yeah, so 8 are unchanged. So 8 are fixed out of 32. So 32 minus 8 is 24. And so all these are bits. So we know it's 2 to the 24. That's how many hosts we can have. Awesome. Maybe in a different network, like my local network, I have the first 16 bits have to be the same. So what I do is I'd call that a /16 network. And I would, so everything that's part of my network starts with the same first 16 bits. So it has to be 192.168 and everything else is in there. So how many hosts would I have in that network? Yeah, good. 2 to the 16. Awesome. What is that 2 to the 16? That should be something that we can calculate and somebody can put in. My keyboard's too far away. Yeah, 65. Yeah, that makes sense. That'll come up later. Right. And then we can have even smaller networks. We can have 192.168.10.1, and I can call it a /24. How many on that network? 256. Yeah, 2 to the 8, which is equal to 256. And the cool thing is, and it becomes a little bit more, so I chose these 8-bit boundaries, right, which essentially line up with the decimal here, the decimal here, and the decimal here, because they're easier to think about. But this could actually, the boundary here between the host bits and the network bits and the host bits can be put arbitrarily. So you can have like a 10 is the other 0.113.0 / you can have in a /11 network or whatever that it can be, let's see, between, no, it can be more than that. Anyways, it can be placed at any bit there. These slides are wrong. I should update them. But anyways, the point is you can put that kind of, because this represents a binary address, you can put that anywhere. Let's see. I chose these. Oh, no, that's right. The 172.16. Is it 168? I can't remember what that is. Anyways, the reason why I picked these, and has anyone seen IP addresses like this, like that start with 192.168.something.something, usually .0.1 or 10.0 or 172? Yeah, what context have you seen those in? Yeah, and your local network, right? So these are all no, not local. It's called the private IP ranges. So you can look this up, and all of these are private IP ranges. So this means that what that means is there will be on the whole entire internet, there is no host that responds to 192.168.0.1. It's guaranteed that there should be no host that does that. The same with the 10 range, and the same with, I can't remember the 172.168. Somebody will have to look up exactly what that that host and net ID is. Oh, Jan is calling me while I'm in the middle of class. Thanks, Jan. I guess found a super. There we go. Do not disturb. Okay. No, you always send Jan to voicemail. Come on, what's wrong with you people? All right. So anyways, that's kind of an interesting point, that this is why these IP addresses are used inside of your network, because we know it's not possible to go out of there. Yeah, so how do you create an IP address? That is a super interesting question. You basically have to ask for one. So you have to, and this is about so this should tell you, because I said there's no 192.168.0. whatever on the wide internet. That means nobody else can actually talk to your local machines, which actually ends up being a good thing. But we'll talk about that later. But yeah, you get so for instance, back up to the diagram, I have a public IP here from Cox. If you go to something like IP Chicken, but whatever you want, there's websites where you can see it. Don't post your IP address in the chat. It's, I don't know, it's better to avoid that. But Cox gives you an IP address when you connect. And similarly, Zoom has an IP address. And actually, we'll see, I need to, and I'll get this in a second. We'll dig in a little bit more, but it's not exactly zoom.com, but let's say it is zoom.com. So through the protocol, and I was going to say magic, but I stopped myself, of DNS. DNS is a protocol that translates a name like zoom.com into an IP address. So this is why we don't have to remember IP addresses. Think about how annoying it would be to remember the IP address of Google or Apple or Facebook or whatever, right? That would be incredibly annoying. So DNS exists such that we don't actually have to worry about that. Cool. Okay, so we have that, how to get addresses. Cool. Let's pop back over here. Okay, so we're going to start with the IP protocol and look at how packets get onto the network from one thing to the other. So we're going to kind of do it in a little weird way. We're going to start in the middle of the diagram, and then we're going to pop down to look at the details there, and then kind of pop back up. But since we talked about IP addresses, so IP addresses are important to understand that there's addresses everywhere on the internet. And the IP protocol really represents kind of the glue. So it provides, and I'm quoting here, I believe, from the RFC, it provides a connectionless, unreliable, best effort datagram delivery service. So what this means is so datagram is just packet is what that means. So we call it a packet in networking. It really is just an envelope of data. You can actually think of it like that. It's just some data that you're sending from your machine to the next machine. Okay, what does connectionless mean? Sorry. Not connected. Yeah, there is no physical connection, but yeah, this means it means I don't have to have a pre-established communication and connection with the other host that I'm trying to send data to. I don't have to establish a connection. So if you and a lot of my analogies are phone based. I'm trying to actually remember, does your cell phone have a dial tone when you just, no, because you have to dial something, right? I guess that doesn't work. Yeah. Anyways, the point is you don't have to establish a connection to the remote system. You can just send a packet of information. You don't have to actually establish a connection, which is kind of interesting. So unreliable, what does that mean? Yeah, it just means exactly what it is. It's kind of like the mail, actually, right? Like the mail does best effort. It tries to deliver your letter, but they're not going to keep delivering it forever. They're not going to hold it around until it finally can be delivered. Your letters can be lost. So this is what the internet protocol provides. Shouldn't say it provides unreliable service, but it does not guarantee reliability. What's the difference between that? Between guaranteeing reliability and being possibly unreliable? Yeah,
it just kind of sends it without putting any protections. You have to do that yourself.
Yeah, so it's and we'll talk about this in a second, but yeah, it does best effort, right? If it was completely unreliable, who would ever actually use this, right? It's kind of it'd be silly. We wouldn't, think about how much of our life uses the internet. And if any of you, I'm sure, especially during COVID times, if you've had an internet outage when you're trying to attend classes, that can be insanely frustrating. Or even worse is when you have unreliable internet where packets get lost. Like, I don't know, I had it where it was happening 10 to 30% of the time of packets were lost, but intermittently. It wouldn't happen constantly. So I'd call the cable company to complain, and they'd be like, okay, we did some stuff on our end, did that fix it? And we would say, yeah, it looks like it fixed it. And then of course an hour later the same problem happened. So that was crazy. Actually, yeah, somebody has a question about a power outage, or not a question, but a comment about a power outage during a final. Do you guys know Fish? Probably not, because he taught this class last semester. Yeah, so Fish, the power went out in his apartment complex, and then he sent us a screenshot of his phone and the Wi-Fi around him. And his was the only Wi-Fi network that was on, because he has his own backup power UPS system. So he was still able to work and get internet during a blackout. So yeah, that was pretty funny. And it also made us realize that, like, oh, the cable company actually must have a different power service, right, than the building itself. So yeah, that was super interesting if you ever want to learn about Fish. Okay, so unreliable, best effort. But now think about this. Okay, so it's the glue of the internet. Let's go back. What does glue mean? Man, I really wish I could go through these slides faster. So let's go here. So IP is in the middle, right? It's actually how the packets get from one place to the other. It seems kind of crazy. So you think about it. So if I were to tell you, hey, I'm going to give you a couple, let's say $1 billion now, you're going to design for me a protocol that's going to be used by literally billions of not just devices, but people. So multiple billions of devices with multiple people who are accessing this protocol. What's your core going to be? Well, I'm going to build you a connectionless, unreliable, best effort datagram delivery service where I'm not going to guarantee delivery, integrity, order. So what this means is I'm not even going to guarantee that that letter that you sent ever gets to the target. I'm not going to guarantee that what you sent gets to the target, right? Integrity, what we talked about. There's no guarantee that the packet that you send actually arrives in exactly the right way or exactly how you intended it. Ordering, I am not going to guarantee if I send one letter and then the second letter, it could be that the recipient gets the second one first and then the first one. Non-deduplication, I won't even guarantee that I won't just make up accidentally multiple letters, that instead the other side, you send one letter, but the other side gets 10 letters. And bandwidth, I'm also not going to guarantee bandwidth. So if you're now put yourself in the funder's shoes, would you be, happy giving $1 billion over to somebody to build what kind of sounds like a crappy system? Yeah, so it's kind of it seems silly. I mean, proposed this way, and it's kind of intentionally so. That's why I did that. But the question is, and we should think about it, what applications am I running on top of that? Right? So I have my internet protocol. What types of things do I have on top of that? Right? So I have, let's think about these properties. Would you want, let's say you're browsing your bank's website. Do you want something that's unreliable and best effort? Yeah, no, that would be very bad. You wouldn't want to click, yes, I'd like to buy GameStop stock, 10 shares of GameStop stock, and actually 1,000 of those requests actually arrive on the other side. And now you're on the hook for whatever 1,000 for a bunch of stock that you didn't actually want, right? That seems crazy. That seems like a bad idea of what you want. Now, but think about other protocols. Let's think about actually this call we're on right now with Zoom, right? So on this Zoom call, so think about what's actually happening right now. Frames of my video are going out from me to Zoom and then back. And let's say each frame currently is a packet, right? These packets come out. What happens to our communication right now if a packet is lost? Yeah, why nothing? Would you even notice? Yeah, there's so many packets, right? They're going one after the other, and my audio is going as well. So maybe if a video call frame is dropped, you wouldn't even be able to tell. Maybe if my audio drops, you could actually pick up based on my mouth what I'm trying to say, right? So, and would you want a video service that guaranteed that every frame got there, even if it meant, so when there was a network problem and a packet got lost, then all my other video waited and waited until you finally got that one frame and then the other frames came up? Right? No, you wouldn't want that. That would actually be a really terrible video service. So this is actually one of these things that's actually brilliant about this internet protocol. It actually doesn't provide a lot of these services. And what that allows, and I'm going to go back to these slides. What it allows is, because this IP layer doesn't guarantee anything, it means that other applications on the top. So I can build a video chat application on the top and not require that every packet always arrive. Think about the other thing, games, right? So the other thing is games, right? How do games essentially work? There's a central server that's keeping track of the entire state of the game. There's all these clients that are sending their status of what they're doing to the server, and then the server is sending them updates on where all the status is, right? And so if I have to wait because somebody else dropped their packet and I'm not getting any other status updates, by the time that packet gets there, it may already be too late. Maybe the user's already done something different. So it seems like on first glance, a kind of a crazy thing of why would you want the core of your networking layer to not provide these really good things? I'd say the one thing they definitely overlooked that they shouldn't have was integrity. That's something that we would want, but they gave us the flexibility to build other types of protocols, and we can actually pick and choose what we need. Do we need reliability? Do we not need reliability? It's super cool. So it's something that looks silly when on the face of it, but actually is very cool. Yeah, and so the whole idea is at the IP level, if I have an IP address, that means I can send a packet to you. So any two nodes, as long as they have an IP address and implement this protocol correctly, and all the other protocols on the stack, as we'll see, they can talk to each other. And that's the magic of the internet. Okay, cool. And so now I'm going to show you, so I mentioned the RFCs, the request for comments. This is a diagram directly from RFC 791. And this is what an IP datagram looks like. And so this is in 32 bits from the 0th bit to the 32nd bit. And we're going to look at this and try to understand. And this is really when we looked at this diagram, this is what gets put here in the address column. So to be able to send it, we need to send a bunch of information. So the very first thing we send is the version of IP that we're sending. So it's the first 4 bits. And think about this. Why is the version the first thing? Wouldn't you think that the thing I care about is the destination? Where is this envelope going? So that should be the first thing, is what's the address? Yeah, so there's some good stuff in the chat. Exactly. So yeah, and this is a really good example of really good engineering of protocols, right? You need to read those first 4 bits in order to even understand the rest of the packet. And this allows us in place upgrades, so we can upgrade to a different version like IPv6, which completely changes how I parse the rest of the packet. But as long as I parse those first 4 bits, now I know how to parse the rest of it. It's super cool. Yeah. Okay. So there's a bunch of stuff in here. I'm not going to get into everything. You can actually read the RFC and learn exactly what everything's for. We have the total length in bytes of the message. We have an identifier, which I'm not sure how deep we'll get into, but we'll see that in a bit, possibly. We have some flags that can get set. So the identifier and the fragment, what happens is when you have that beautiful layers, the marketing, hello. Okay. So the marketing here is, at the internet level, you only need to care about IP. So an IP packet can be as big as, I think it's 65,000 bytes. So it was 16 bits, right? So 2 to the 16th was 65,000. So it can be 65,000 bytes. Now, the question is, can your actual layers that transport that information, can Wi-Fi packets and frames be up to 65,000 bytes? Maybe it's not bytes, maybe it's bits, but whatever. It doesn't really matter for the point here. Yeah, it seems like it's too big, right? and actually Ethernet. So you think Ethernet, I don't know about you, but as soon as the pandemic started, I basically switched everything over to Ethernet. And I should have like massive cords running throughout my house. Since I'm on Zoom constantly all day, I don't want to deal with any jitter from Wi-Fi or anything. So, but IP Ethernet frames are capped at 1500 bytes total. So what actually happens is the IP layer tries to send a packet, and then the link layer says, hey, I can't send, or the physical layer even will say, I can't send this. This is way too big. So IP itself has to have a mechanism to deal with it. So that is where we get the, that's where we get the identifier and the fragment. So there's actually a way that the operating system can say, oh, this packet's too big. I'm going to split it up into a number of different. So it's like taking a huge envelope that you're trying to send, cutting it up, and now you need to put on that envelope, okay, which one was the first one? And they're all from the same envelope. So I'm going to put the identifier here that identifies that each of these fragments are part of the same envelope. And then I need to know the offset. So the one at the start will be the 0th offset. The one 10 bytes or 1500 bytes after there will be the 1500 bytes. And anyways, so that those this information can all go out, and then the other side can get it and receive all of them. We have another field which sounds really cool, and that kind of is the time to live. So, we talked about that the mail doesn't just like hang on to letters forever. I guess, why doesn't the mail system hang on to letters and just keep trying to deliver them? Yeah, it gets full, right? So now think about, I'm sending packets into the internet and it's just like floating around. Or what actually, can happen is an infinite loop where packets actually go back to the same place and they get stuck in this loop. And, technically they could just like stay there forever, but eventually they'll overflow things and packets will drop. So to prevent that, there's a field called the time to live field. This is actually used for network reconnaissance, which we'll talk about later. But the idea is, this is the number of hops. So specifically, like here, a hop would be from my machine to the router, and then the router to Cox, and then Cox to somewhere else, and over here. All of these, and you understand networking when you really in your bones understand exactly what happens in each of these hops, and we will go over that in this class of what's going on here. So at every hop, that time to live value is decremented. So it starts high, and then at a high level, and then gets decremented down. And then when it hits 0, the router that has it like drops that packet and says, okay, I'm not going to deal with this packet anymore because its time to live value is too low. We have something that says the protocol, and we have a checksum of this header. So we'll talk about that in a second. And then we have the source IP address and the destination IP address. These are just like the letters that we're used to talking about in the mail. We have a 32, but in this case, it's a 32-bit number with source IP and a destination IP, some options, some padding, and then finally the data of the header. So you can see we actually have a decent amount of overhead on this packet of information that has to be there. So the header thing has to be there. I claimed that there was no integrity on at the IP level, yet I see there's a header checksum. So what's the difference between a checksum and like an integrity check? Yeah, so checksum is a checksum is some kind of algorithm that let's say XORs all the bits of the packet and make sure that at the end it's 1. That would be one type of header checksum. I think the way this works is it XORs everything together and make sure that it equals whatever in the header checksum. But basically what it means, and checksums are good at detecting if one bit is flipped. And actually, anybody do any work or deal with credit cards at all? Yeah, so credit card numbers themselves have I think it's a Luhn check, LUHN or something like that. Somebody can link it in the chat. The Luhn check is a way that you can actually verify if a credit card is a valid looking credit card. So that way people can detect when if somebody has accidentally input the wrong credit card. Yeah, that algorithm is basically a checksum. So checksums are good for a specific, testing if a bit is flipped. But part of the problem with a lot of them, if one bit flips one way and the other bit flips the other way, it doesn't detect that. And fundamentally, an attacker can overwrite the header checksum or do anything they want to do to this packet. Cool. Okay. So we have this. Okay, cool. And so this is all that information that goes onto your packet. Wait for me to skip. I got to figure out this iPad better. Anyways, okay. So the way this basically works is your IP packet will then get incorporated into the lower levels, and we'll actually look at what those look like in a second. So we have your IP header and your IP data go into the link layer. So they become the frame data, and your frame data adds another frame header. So what actually arrives has all of these headers on it with the actual data as part of it. Okay, now we're going to look at the case of. So now we know roughly, we have a rough idea and understanding of, okay, this looks pretty easy, right? I know if I have, if I know my IP address and I know Zoom's IP address, I could make a packet using all that information I just said and send it out and get a packet to them, right? We're not quite there, but we have our goals in mind, right? We want to be able to send a packet there. But what we need to take care of first, so as the packet goes from us to Zoom, it has to first go from us to our router or our switch, and that is called direct delivery. So, and this gets back into. This actually gets back into these IP address ranges. So when a machine, so you're a machine, your machine boots up. We won't get into it, but there's so DHCP is just a protocol where your machine, when it boots up, can say, your computer says, hey, I need an IP address. I don't have an IP address. And then your router will actually listen for that and respond and say, okay, hey, new machine, your IP address is this, and it will give you an IP address. Or you can configure your computer with a static IP address. So you can say in your settings, my IP address is 192.168, and we'll talk about all the information you need. Can you hear me now? I was like USB lost. I don't know what happened. Maybe I accidentally unplugged my mic. Okay. All right. So for us to exist on the network, we must have an IP address. So my machine boots up. I use DHCP and I say, hey, I need an IP address. I don't know what my IP address is. And somebody responds 192.168.0.10. We'll go with 10. Okay. That's one piece of information I need. What is my IP address? Now, going back to this diagram. So I have my IP address, great. But I need to know when I'm sending data, am I sending it to my my, let's say my Xbox on my local network? Am I sending it to my switch or my router? Who am I sending it to? Or am I sending it to Zoom? And the difference, as we'll see, basically the difference is who's on my local network where I can just send packets to directly versus who do I have to send it so that it hops to some other network. So what we also need is a way to tell who's on my local network versus who's not on my local network. And that's with this exact thing that we just talked about of these IP addresses. So your computer, the DHCP address, or if you're setting up static networking, will say this is your IP address. So it'll tell you the IP address and it'll tell you the network. Now, I'll go with the /24 for now. So this has a couple different names, which can be very confusing. It could be, if you're looking at it, net mask, or CIDR is one term that you'll see. But it's basically a way, we'll always do it in this format because it's very easy. The net mask version actually shows you all the bits that are 1. So it'd be all 8 ones is 255. So it'd be 255.255.2, almost got it, 255.0. And what this net mask means is if you take that integer and you AND it with an address, that tells you if with your address, that tells you what your network is. So it means the first 24 bits are all 1. But the most common way of seeing it is in this kind of /24. Actually, let me look at my computer real quick and see how it shows it. You may have to go into like advanced TCP/IP. Yeah, so mine has my IPv4 address and my subnet mask, which shows me 255.255.255.0, which is exactly what I thought it would be. Cool. So now with this information, so now if I know, okay, this is my IP address and this is my net mask /24, now my computer has all the information it needs to be able to answer the question, like, and so now anytime my computer wants to send a packet, so it says, okay, hey, I have a letter here for, so the destination IP here is 192.132.0.100. And so now my computer has to ask local. So is this IP address on my local network? If no, or if yes, why? Stick to your guns. So it starts with 192. So what this /24 means, where's the network boundary? Right here on this octet. So this means this is the network, local network. And this is the host. So this means the first 24 bits have to be exactly right. Yeah, great. So we'd look here, we'd say, is this the same? 192.168.0, 192.132.0? No. So it'd say not local. And then we'd figure out what to do there. We'll talk about it in a second. Okay, great. What about, kind of like up there. What about, I want to send a packet now to 192.168.1.10. Is it local? No. 192.168.0.110. Yes. Excellent. Okay, cool. And you could see that by changing, I could change Now, if I change this to a /8, would this be a local address? Sorry, you can't see where I'm posting. Now we'll ask these questions again. So now it's a /8, is 192.132.0.100 local? Yes. What about 192.168.1.10? Yep. And 192.168.0.1110? Yep, all three are. And now I'm going to do this one more time just to drive this home. Or actually, I'll just leave this here and you can figure it out. So now if it's a /16, which of these are in and which ones are out? Okay, cool. Now you're understanding the first step of networking. So I want to send a packet. I know the address. I want to send an IP packet. I need to know, is it a local address or not? And this is how we can tell. Because if it's local, then we do direct delivery. So yeah, here's an example. So the network, this is another way, a third way of representing the net mask. This is saying the subnetwork is 111.10.20. This means, so that we, in our parlance, we'd say this is a /24 because everything that begins with 111.10.20 is in the same network. Okay, so we have we'll get into the MAC addresses in a bit, actually just in a second. So I'm machine 111.10.20.121. I want to talk to 111.10.20.14. And so I'm going to make that IP packet just like we talked about. I'm going to say, great, I know you're on my local network. That means I can send this packet directly to you. So anyone on my local network, I should be able to send a packet to, and they should be able to receive it. But I need to know how to actually send that to them. So those other numbers underneath is, so the subnet mask needs to be the same for every machine on our network. Otherwise, we won't be able to talk to each other. So the subnet mask is for all the machines. So they all are in a /24, so they know from their IP address they can derive the subnetwork. Okay, but I need to actually send it at the link layer because we've only been talking about IP. So we're going to get into these other. We actually have another type of addresses that address your essentially your network card at the link layer. So that has to get out. So now we need to go dig into the link layer to figure out how to do that. And I usually never do this, but I will, since you got a midterm coming out today, I will let you out early. Feels weird. I feel like I don't like it. No, everyone come back in. We'll keep going. I'm just kidding. All right. So we'll stop here at Ethernet frame and we'll, now we got a lot to dig in here. I don't think it makes sense to power through. So yeah. We'll come back here and I'll see y'all here on Monday, and I'll see the people who are watching this on Thursday on Tuesday.